Deep inside the oak wood is the acorn hoard. Everything here is weighed and measured to survive the winter. Our resident gatherer is Hazel, the red squirrel. She tracks her hoard using nesting trays, but her weights are not identical. She has tenths of ounces mixed with hundredths. If she combines these different resolutions blindly, she will miscalculate her winter supply entirely. To accurately combine or compare these different weights, she must rely on a strict mathematical law. She has to work place by place. She sorts the physical trays and slides them together so that tenths sit directly over tenths and hundredths rest exactly over hundredths. Look at the leaf, 4.37 plus 2.8. The hundredths place is empty under the 7. We drop a 0 placeholder, making 2.80, aligning the decimals. We add place by place. The result is 7.17, the point dropping straight down. This strict place value alignment is the only way to combine data of different resolutions. Without it, you end up adding tenths to hundredths, throwing off the value of the entire hoard. Taking weight away requires that exact same precision. Let's say Hazel has a reed weighing 6.25 ounces and needs to trim off 2.48 ounces. Notice how 6.25 is stacked directly over 2.48. The decimal points must be anchored into this vertical guideline before doing any math. We subtract place by place from right to left, regrouping exactly as with whole numbers, leaving us with 3.77 ounces. Subtraction demands point-under-point alignment because you can only reduce an amount accurately when identical units interact, taking hundredths from hundredths and tenths from tenths. When we shift from combining weights to scaling them, the rules of decimal arithmetic change. Let's look at the multiplication problem, 3.6 times 0.4. We temporarily bypass the decimals and multiply the factors as whole numbers. 36 times 4 equals 144. Next, we count the total decimal places in the original factors, 1 in 3.6 and 1 in 0.4. We place the point 2 spaces over, giving 1.44. Scaling operations don't rely on vertical alignment during calculation. Instead, we aggregate the total decimal resolution of the factors to define the product's final scale. Our final operational requirement is equal distribution. Hazel has 0.96 ounces of acorns that she must share evenly into 4 distinct caches. Before sharing begins, the decimal point travels straight up from the 0.96 and locks into position on the quotient line. We share the 96 hundredths equally into the 4 caches, leaving 24 hundredths per cache, written around our anchored point as 0.24. Division is the process of distributing equal shares across fixed, pre-aligned place values, ensuring the structural integrity of the data remains intact. Look at the numbers generated: 7.17, 3.77, 1.44, and 0.24. When alignment rules are strictly followed, the decimal points form a flawless architectural column. Line up the points, add zeros to match, and work strictly place by place. This mathematical alignment extends far past the oak wood. This exact structural rigor drives global financial systems, precise scientific measurement, and physical engineering. With all the math verified and aligned, Hazel's woodland hoard is now perfectly balanced, and her winter cache is completely secure. Line up the points, and the places fall naturally into place. I'll see you at the next bend. But before you go, look at this equation, 5.4 plus 0.36. When adding these amounts, where exactly must the 0 go, and which places must align?